Okay, this video is about mathematical induction, and we're gonna see what is the actual difference between this and the strong mathematical induction. But before, I'm going to do a question that can be done using, let's say, normal induction, just to refresh your memory. And then we're gonna go and do, the strong mathematical induction. Okay, so here we go. So we're gonna say mathematical induction. Okay. All right. Let's consider this example. All right, so in here we're gonna do this. So prove that the sum from I equal 1 to n of I square is equal to n plus 1 2n plus 1 and then over 6 all over z. Okay, so we are going to prove that that is true, come up for all n in n. Okay, so what we normally do, we do 3 steps. Okay, so it's like prove, and then what we normally say is like let p of n equal to the left hand side, so it's this expression, and we call q of n the right hand side. Okay, so what we actually need to prove, we need to prove that p of m is equal to q of n for all n in n. Okay, so first step, when n equal 1, okay, so we're gonna say for n equal 1, for n equal 1. All right, so we're gonna check and see if the left hand side is the same as the right hand side. So we're gonna say p of 1. P of 1 is the first term on this sum, so it's just gonna be 1. And q of 1, let's check, that is gonna be equal to 1 multiplied by 2 and then multiplied by 3 divided by 6 is also equal to 1. Okay, so then conclusion, then p of m is equal to q of n for n equal 1. And then what we do, this is where we need to pay attention, okay, because you're gonna see that this is where the difference is in between mathematical induction and strong mathematical induction. Okay, so what we normally say, we are assuming that this proposition here is true. So for some value of n, let's call it k. Okay, so we are assuming that this proposition is true when n is equal to k. Okay, so that means that we are assuming that p of k is equal to q of k. Okay, so that is our assumption. Okay, so here we're gonna say k obviously have to be greater than 1, and have to be a natural number. Okay. We already did, the n equal 1, so that's why in here, actually, we need to say k greater than 1. Okay. Okay, and then we check that this is also true for n equal k plus 1. So we're going to say for n equal k plus 1, we're going to show that that proposition is also true. Okay, so here we go. So we're going to say p of k plus 1, by definition of p, is going to be equal to the sum from r equal 1 up to k plus 1 of I square. Okay, so this means 1 square plus 2 square plus 3 square all the way up to k plus 1 square. Okay, and then what we're going to do, we are going to split this into k, and then we're going to take, the k plus 1 terms out. Okay, that's what we've done previously. I'm going to make more room. So let me do this. Okay. All right, and this is the same as pk by definition. So this is p of k, and this is k plus 1 square. But we know that p of k is the same as q of k. Okay, so this is q of k by our assumption. So we can say that is equal to that. But then we have an expression for q of k, which is equal to k plus 1, 2k plus 1 divided by 6, and then plus k plus 1 square. Okay, and then with a little bit of algebra, we can say that this is equal to, I'm going to take k plus 1 as a common factor, and that will leave out 2k plus 1, and then in here we're going to put plus 6k plus 1, all the brackets, and then we can divide everything by 6. Okay, all what I did is just amplify this term by 6, the top and the bottom. Okay, and then we can put this together. All right, and then I'm gonna make more room again. Okay, and then when you simplify this, let me see, I think I put an extra k in there. So that doesn't go there. Okay. All right, and then we're going to have k plus 1 in bracket, and then inside of the bracket we're going to have k squared after simplifying plus 7k, and then plus 6 all over 6, and that will simplify to k plus 1, and then it's going to be k plus 2. Okay, so this is a trinomial, okay, quadratic trinomial, and then that will simplify to that, which is then 2k plus 1 plus 1, so it's going to be 2k plus 3. K plus 3 divided by 6, and that Okay, let me shrink this a little bit more. Okay, and then I'm going to make this smaller. Okay, and then this is exactly equal to q of k plus 1. Okay, so therefore we can say about mathematical induction, P of n is equal to Q of n, comma, for all n in n. Okay, so this is the traditional mathematical induction that we done previously. Okay, and you can see that it works all right. But then we're gonna see where is the strong mathematical induction. Okay, so I'm gonna stop this video here, and then I'm gonna start a new one.